this chapter, we're going to start looking at applications of derivatives. In this lesson, we're going to focus primarily on velocity.
All right, everybody, so here we go. We're talking about velocity specifically, but what we're really going to do here is we're going back and we're talking about motion. It's just that in this question that we're going to look at, and really is all I'm going to do is I'm going to work you through kind of this one fairly lengthy problem here, but it's all kind of velocity related or ish. We're kind of using velocity as a stepping stone. We're going to talk about a few things here. Anyway, so our problem says that for the position function s of t is equal to t cubed minus t squared plus 24t, where t is in seconds and s is in meters. First of all, find when the particle is at rest. Okay, now we're going to just do these things one at a time here. So A, we're going to find where the particle is at rest. Now, what does that mean? Okay, and so you need to think about this, and when you get a question like this, you need to really think through what the question is saying, so that when you do the math, you're modeling what the question is saying, so that you can then determine the unknown. So in this case, I'm looking at when. Okay, so I'm looking for time. Time is what I'm going to solve for. When is the particle at rest? Well, what does that mean? Well, in this case here, that means that the velocity is equal to 0. Okay, well, I don't have the velocity. What I have is displacement. Okay, this is what I've got. But the nice thing is I know that the derivative of displacement is going to be velocity. So the derivative of displacement here will be 3t squared minus 18t plus 24. Okay, great. So now I've got an expression for velocity. This is equal to my velocity. So all I'm going to do in this step right here is actually make it abundantly clear that what I'm looking at here is in fact velocity. Okay, now we're going to take that and set velocity equal to 0. This is going to be when the particle is at rest. So I've set it equal to 0. Now I can see that each one of these terms here has got a factor of 3 in it, so I'm going to divide everything out here by 3. So I'm going to divide both sides by 3. That's just going to get rid of it completely. So it'll be t squared minus 6t plus 8. And then I will factor that, and it works out nicely here that this is factorable. Now if it wasn't factorable, then what we would do here is we would use the quadratic formula, but in this case it works out nicely here. So I'm going to get these two little factors here, t minus 2 multiplied by t minus 4. Well, those are going to go to 0 when t is equal to 2 or t is equal to 4. So at 2 seconds and 4 seconds, the particle is at rest. Now, that's going to become important later on for some of these other questions that we're going to look through. Anyway, question B. When is it moving in the positive direction? Okay, to be moving in the positive direction, or to understand what that's saying, we need to understand all of this in terms of the vector quantity here, okay? So here's our number line, and here's going to be our origin. To be moving in a positive direction, in most cases, just by the way we define it, typically means we're going to be moving to the right, okay? So we'll draw our vector here for velocity, and as long as velocity is positive, we are moving in a positive direction. In fact, that's exactly what that means. When velocity is negative, we are moving in the negative direction. Okay? Now, again, make sure that you're understanding that different than speed. Speed doesn't have a direction with it. Velocity has both direction and magnitude. So now, we've already got an expression for velocity. We know that velocity is equal to 3t squared minus 18t plus 24. And so what we want is we want this expression right here for velocity, 3t squared minus 18t plus 24. We're interested in where this is greater than 0. Okay, in the intervals where this is greater than 0, then this particle will be moving in the positive direction. So now, here's the moment. Okay, here's that moment way back when you did questions like this where you were looking at quadratics and determining where is the quadratic above the x-axis, where is it below the x-axis. Then when am I ever going to use this? Here's the moment you're going to use it. Okay? So when this function is above the x-axis, that's where this thing is moving positively. Where it's below the x-axis, that's where it's moving negatively. So now, we already factored this. We know that we can take out a 3, and that when we do that, we're going to get t minus 2, t minus 4, greater than 0. Okay, so I know that this is going to go to 0 at t is equal to 2, t is equal to 4. These are my zeros. Okay? Now, I'm going to use what I know about parabolas to answer this question. I know, okay, here's my number line. I know that this is going to be a parabola that opens upward because the leading coefficient is positive. And it's going to have x-intercepts here at 2 and 4. So this thing's going to come down and then go back up. I know that. Okay, because of my previous experience with parabolas. So I'm going to use that information to make this question easier. I could make this harder by trying test points and kind of going slowly through this, but I can see right now where that's going to be, how that's going to interact with the x-axis, and I'm going to use that to answer this question. So I'm looking for where this parabola is above the x-axis. Now that's going to be here in this interval. And in this interval right here. On the interval in between, it's negative. It's below the x-axis. It dips down below here. So I know that my velocity, or the first derivative of displacement here, this is going to be positive, okay, when t is less than 2 together with t greater than 4. And that's awesome, except for one small detail, okay? And if you were to answer like that, like if you were one of my students and your answer like that, I'd be really happy, but I would still dock you, because anytime we do these questions, there's this implied restriction that time has to be greater than 0. So this actually isn't an arrow that points all the way left. It actually stops right there at 0. And in fact, as I come forward to 2, notice that I'm not even going to include the 2. I'm also not going to include the 4 because that's where velocity is equal to 0. And I'm not asking for that. I'm asking specifically, where is it positive? Where is it moving in the positive direction? So my answer here is really going to be 0 less than or equal to t, less than 2. Okay, union, because I want the union here, t greater than 4. Okay, now, notice I'm not including the 2 and the 4 here, but I am including the 0. Okay, so I'll just zoom in on that. I am including the 0 here. Now, that's because, based on this scenario here, this thing does have a velocity at the initial time, when time is equal to 0. In fact, if you look at your velocity function right here, if you let t go to 0, we're going to get that our velocity is positive 24. So this is kind of like a car race, okay? The cars are going around the circle here, but when the flag drops, they're already moving. So at the beginning of the race, they're already moving. That's the same sort of thing here. So at time equals 0, it's got some forward velocity. At time equals 2, it stops. At time equals 4, it stops, but then it starts to move forward again. Now, in interval notation, this would look like this. Okay? And you want to get comfortable with interval notation. Okay, so 2 different ways of writing that. Good. Whoops, wrong way. Okay, let's take a look at the next question here. C, find the total distance traveled by the particle after the first 7 seconds. Okay, total distance. Right. I am asking you for distance, but the function that I've given you is displacement. Okay. Now I realize that the purpose of this particular lesson is supposed to be velocity. And it is true that this particular question actually doesn't have all that much to do with velocity. But there's something that we're going to look at in a couple of minutes here where this information is actually going to be sort of important here. So if I want the distance, okay, I need to remember that this right here is a scalar. What I've got is displacement. And this is a vector. Now, the reason why that's an issue is because my displacement is going to be direction sensitive. Okay? So my displacement, when I'm looking at the number line here, if this is my origin, my displacement is always measured from here out. Okay, from here to there, from here to there, from here to there. Distance, however, isn't. Okay, if you're going along that number line here, distance, I go out to here, and if I stop there and change directions, then I start to measure it from there again. Stop and change directions, well then I'm measuring it from there again. Stop and change directions, I'm measuring it from there again. So my starting point when I'm measuring distance always resets to wherever I'm stopped. With displacement, it doesn't. You always measure it from that one initial starting point right here. So what I need to do here is I need to just think about how I can convert displacement into distance. And actually, it's not that hard to do. So what we're going to do here is my distance, okay, first of all, bear in mind that my particle here stops at 2 seconds and 4 seconds. Now, what that means is, now think about when the velocity stops here, what's going on here. When I throw something up in the air, now I'm going to, I'll do this horizontally here, but if I throw something up in the air, okay, it goes up, it comes down, okay? I give it forward or upward velocity, it goes up, it slows down, right up here, it stops, just for a infinitesimal moment there, it stops, and then comes back down again. But the reason it stops here is because its velocity is positive, okay? Velocity is positive, it's a large number, but it's a number that gets smaller and smaller and smaller as it gets up to here. Eventually, it's got to become negative velocity to come back down again. So it's got positive values that are getting smaller, and then it's negative values that are getting larger. At some point here, it goes to zero. It goes to zero when it's changing directions. Okay? Now, because displacement is always measured from the one spot here, what happens here in terms of my vector is my displacement gets larger up here, stops changing, and then displacement gets smaller. Distance doesn't work like that. Distance works like this. You throw something up, distance gets larger. I'm changing directions, but I'm going to change my starting point. Distance gets larger. Okay? So distance is always increasing. So what I'm going to do here is I'm actually going to figure out what the displacements are in those different sections between the places where the particle changes directions. So the particle's moving. We've already established the particle moves forward for the first 2 seconds, comes backwards for 2 more seconds, and then goes forward again. So at the 2-second mark, it's changing directions. Well, I want to know how far did it go in those first 2 seconds. Well, that's going to be the difference between the displacement at 2 seconds and the displacement at 0 seconds. Okay? When you subtract those, that's how far it's traveled. But I use absolute values there, everybody, because displacement can be negative. Okay? And if the change in displacement is coming back towards the origin, that's going to be negative, like it will be in that second section. Okay? So it's also changing directions at the 4-second mark. So I want to know what the displacement is at 4 seconds and subtract the displacement at the 2-second mark. Okay? Because it went from 0, it went up to 2 seconds, then it changed its directions. Now I want to know what this change in displacement is. Okay? Then my last little section right here is going to be to determine what the displacement is from 7 seconds down to 4 seconds. And again, I take the absolute value of that. Now, where sometimes this gets hard for people to do is when they start to try to plug this all in, they go right back up to your displacement function, and they start doing this one little bit at a time because you're using that function over and over and over again. Let me show you what you can do here to make your lives just a little bit easier with your calculator. Okay, so here's, oops, sorry, get rid of the reflection there. So here's the calculator. I'm going to do all of this right away in one step on my calculator, and I do that by going to y1, and I'm going to enter in my function here. So t cubed minus 9t squared plus 24t, or x in this case here. So I'm going to enter that in, and I enter that into y1. Then I'm going to quit. Okay, I want to get out of there. So I'm not going to graph this. I'm going to use what I know right here, and enter that into the calculator. Now, first of all, I've got the absolute value, so I'm going to press math over to num to grab the absolute value, and then I'm going to actually enter in this function notation. Okay, my function, if I press the vars button, okay, that takes me into a menu here where I can see all the variables that the calculator uses, and I'm looking at a y-vars. I'm going to choose function because that's what I entered in here. I'm going to use y1 because that's where I put my function. 0, 2. So this is y1 evaluated at 2. This is function notation. Minus, I'm going to do that again. So here we go, vars over to y-vars. It's a function, y1, evaluated at 0. I'm going to add to that math, absolute value, and then I'm going to do vars, y-vars, function, y1 of 4 minus vars, y-vars, function, y1 of 2. Get out, and I'm going to add math, absolute value, vars, y-vars, function, y1 of 7, minus, last one, vars, y-vars, function, y1 at 4. And so I can enter that whole thing in one step here, and I don't have to keep re-entering the function over and over again. I mean, I'd have to do it 6 times here. Press enter, and I get that the total distance traveled here was 78. Okay, excellent. Excellent. Now, if I had done that piece by piece, you're going to see that there's some information that would have been useful to have had, or it will be useful to have, but we'll get to that when we get to that particular problem in this question here. Now, let's go back up. Let's take a look at D. When is the particle moving towards the origin? Now, that's an interesting question. That is an interesting question. When is the particle moving towards the origin? So here, let's take a look at the number line. Put the origin right here. Okay. Now, let's just think about the scenario here. Let's say that for right now, here's where we're located. So I am to the right. So here, in this case right here, my displacement is positive. Now, if I'm going to be moving towards the origin, okay, to move towards the origin, that means my velocity would have to be 0. Sorry, not 0, less than 0. It would have to be negative. I'd have to be moving to the left. Okay? If I'm moving to the right, then I'm going to be moving away from the origin. So velocity would have to be negative if my displacement is positive. Now, the other scenario that's possible here is I could be over here, in which case my displacement is negative. I'm to the left of the origin. If I want to be moving towards the origin, then my velocity has to be this way. My velocity has to be greater than 0. So notice the scenario that we've built here. In order to be moving towards the origin, it has to be the case that if displacement is positive, velocity is negative. And likewise, if displacement is negative, velocity must be positive. So we see that if you've got velocity times displacement, that when those are opposite signs here, you're going to get a negative result, and when that's true, you're now moving towards the origin. Okay? And if it's positive, you're going to be moving away from the origin. But in this case here, we're asking where are we moving towards the origin. So we want to know where that product is going to be less than 0. Now, please don't go and ask your physics teacher, what is velocity times displacement? What does that mean? It's just a mathematical tool that we're using to take advantage of the relationship between the signs here. Okay, that really doesn't signify anything. Okay, so now we're going to multiply velocity times displacement. So we already know that that's going to be 3t squared minus 18t plus 24 multiplied by t cubed minus 9t squared plus 24t, and we want this to be less than 0. Okay, now whatever you do, don't expand that. Okay, because if you expand that, you're going to make that much more difficult than it needs to be, particularly to see what the graph is doing. Really what I want to do is factor it. Now I already know that velocity will factor down to 3 multiplied by t minus 2, t minus 4. I've done that already. And then here I can take out a common t. We'll just do this in steps here. Okay, so now I want to see if I can factor this t squared minus 9t plus 24. Okay, so it's just a quadratic, so I'm looking at factors of 24 that add to negative 9. So what do we got here? 2, 12, nope. 3, 8, nope. 4, 6, okay. Doesn't look like that's going to factor nicely. Now, that's not a problem. It's not a problem at all. That just means that I might have to use the quadratic formula. And that's not a big deal. That shouldn't even cause you a moment's hesitation. Just, can't factor, jump right in. Now, but I'm a little bit on the lazy side, so I'm just going to take a look really quickly at the discriminant just to see if I even can factor that. So negative 9 squared minus 4 times 1 times 24. And when I plug that in, that's going to be negative, it's going to be positive 81. What do we got here? Minus 90, oh, okay, yeah, so it's going to be negative 15. Okay, so the discriminant's going to be negative 15. That tells me that I'm not going to get any real roots for this thing going to 0 here. So that's actually a neat result, because that means that my only zeros here, the only places where this product goes through 0 is 0, 2, and 4. So when you take a look along the number line here, it's going to be 0, 2, and 4. Now, I can take advantage of what I know of how polynomials behave. Now, first of all, I've got a quadratic multiplied by a cubic. So I know this is going to be a fifth power. I know that when the leading coefficient is positive, and in this case it would be because I've got a positive 3 and a positive 1, that this is going to go up. I also know that the multiplicities of these factors here are all 1. So that means that the multiplicities of the roots will all be 1. So it's going to come up, it's going to come down, it's going to go up. And now, and at some other place here, it's probably going to do another little wiggle. Like it's probably going to do some other little wiggle up here because of the quadratic right there. But like I don't know, and it's not really all that important for this problem. So here's what this function is going to look like roughly around the x-axis. So where is this function, where is the product of those two negative? Well, the product of these two is going to be negative from negative infinity up to 0, and then including the interval between 2 and 4, which is great, except that this part doesn't make any sense because I'm talking about time before 0. So actually the only answer is between 2 and 4. So this is going to be moving towards the origin, okay, on the interval from 2 seconds to 4 seconds, okay, or 2 to 4 if you want to write it like that. Whoops. Okay, and I'm going to use the parentheses there because I'm going to assume that we're not interested in the spot where it stops. Okay, so there you go. I hope that makes sense there. And again, remember, that doesn't have any kind of a physical significance. It's just we're utilizing the fact that they have opposite signs so that I know that the product will be negative regardless of the scenario. Build this little product here. Hopefully it breaks into factors nicely. If it is broken into factors nicely, I would just include those factors here, give myself a plot based on what I know about a polynomial, and take it from there. All right, now the last thing that we wanted to do was to draw a schematic of the motion. Now, what we mean by that is we want to draw a little diagram here that gives us a sense of the direction that it's moving, and then we're going to label it with the values of the displacement and time and velocity so that you get a sense of what's going on here. But bear in mind that this is simply one directional motion. The particle is simply moving forwards and backwards, okay? It's not moving along in the plane. It's like it's on a railroad track and it's going forwards, backwards, forwards sort of thing. So what we're going to do here is I'm going to give myself a little bit of room here. I'm going to start kind of in the middle of the page here. Here's my origin. Now, I know, based on the work that I've done already, that this thing is moving in a positive direction on the intervals 0 to 2 seconds, 4 to infinity there. So I know that for the first 2 seconds at least, okay, it's going to start here, okay? And actually what I might want to do is I might want to figure out what the initial, sorry, I shouldn't even put that there. I'm anticipating where the result is. Shouldn't have done that. I don't know that it actually starts on the origin. I'm going to put the origin right there. I got to figure out what my initial displacement is. Now, the nice thing is I've already got, whoops, I've already multiplied in there. I needed to check the last result here. Whoops. So I had put the velocity in there. Whoops. Well, that's what I wanted. Okay. So here's my displacement function. I'm having a hard time getting rid of that thing. There we go. Here's my displacement function. So t squared minus 9t, t cubed minus 9t squared plus 24t. I want to figure out what my initial displacement is. So vars, y vars, function y1. I want to figure out what that is at 0. It's 0. Okay, so we are starting right on the origin. Okay, that's important. Okay, that's important. Now, my first bit of motion is to move positively. I know that from 0 to 2 seconds, it moves positively. Now, how far does it go? Okay, how far does it go? Well, I don't know. Let's figure out what the displacement is. Whoops. Let's figure out what the displacement is at 2 seconds. Now, I'm going to go up to here. I'm going to steal that, put a 2 in there. So my displacement is 20. So for my first 2 seconds, it's moving to the right, and then it's going to change directions. It's going to come back around. Now, right here at this moment, I know that my time is 2. I know that my displacement is 20. Over here, at the beginning, I knew my time was 0, and I knew my displacement was 0. Now I'm going to fill in velocity here in just a second, but I'm going to keep working like this. So I know that it changes directions at 2. Now, let's figure out what my displacement is at 4 seconds. 16. So that means, and remember, that is measured as the distance from the origin out here. So at 2 seconds, I'm out at 20, but at 4 seconds, I'm back here at 16 away. So when t is equal to 4, displacement is equal to 16. So I came back a little ways. Now that makes perfect sense because I already knew that on the interval between 2 and 4 seconds, because of this setup, that it was moving back towards the origin. And in fact, that is exactly what I'm seeing. Moves back towards the origin. Now, in this particular case here, we were asked to draw this out up to 7 seconds. So I now got to figure out, well, what's the displacement at 7 seconds? So let's go back up here. And I'll put in a 7 in there. 70. Okay, so it goes quite a ways out here. So my scale is going to be a little bit off, but you get the idea. So it's going to go out to here. And so at 7 seconds, my displacement is going to equal 70. And I probably should have units here. Seconds, meters, seconds, meters, seconds, meters, seconds, meters. Okay, and the particle is moving to the right. And again, I knew that because I knew from 4 seconds on that it was moving in the positive direction, so to the right. Now, to finish this off, I would like to include my velocity. So I'm going to go to y equals, okay, I'm going to put my velocity function here, which I know is going to be 3x squared minus 18x plus 24. Okay, and I'm going to quit, and then I'm going to do this. I'm going to go vars, y vars function. Now in this case, it's y2. That's where my velocity is. So I'm going to choose y2. And my initial velocity, where y2 is equal to 0, is 24. So initial velocity is 24 meters per second. Now I'm going to go up and let's figure out what the velocity is at 2 seconds. 0. And I knew that. I knew that was 0 meters per second. I also know that when I get to here, I mean, I could do it on the calculator, but I just showed you here. I already know that this right here is going to be velocity is equal to 0 meters per second. What I don't know is what the velocity is at 7 seconds. And way out here, my velocity is going to be 45 meters per second. And that's what we mean by a schematic of the diagram. Of the motion here. So I know what direction it's going, I see how far it goes, and I label here when it stops. So I can see when it's coming back towards the origin, when it's going away from the origin, and so on. Okay, I hope that makes sense. What we'll do here is I'll put together another lesson for you where we focus on acceleration. But what you're going to see is a lot of the same sorts of things that happen here, where the relationship between velocity and displacement is in many ways paralleled to the relationship between acceleration and velocity.